No, they're both straight chain. They're not going to be cyclic.
This is cyclohexane.
Yeah, and that's just the solvent for this stuff. It's just dissolving. It's not part of the polymer at all. Okay. This stuff that we use, the reason that we don't just use it straight, we have to dissolve it in cyclohexane. We buy it, oh man, I think we buy 100 milliliters at a time. 100 milliliters is not very much. I'm just looking for 100 milliliters is just about the volume that will fit into this. In fact, this may be a little bit more than 100 milliliters. It costs more than $100 for this much of this compound. It's not this specific compound, but the diacid compound we're going to use, semicolloid chloride, is super expensive. So yeah, we use just a tiny little bit of it so we can make it last. We've got 8 sections of this class. I want to make sure that everybody can get at it. And we still have money for other things we want to do in the class, right? But it's a great lab. You're going to really like it. Okay, now the other type, so those are both polyesters, polyamides. Those are called condensation polymers because they involve condensation reactions. This is going to be a different kind of reaction. The addition polymer is completely different. I'm going to give you a chance to write that down. Understanding there's going to be a term up there that you don't understand. Okay, you ready for this? So you have this word up here, radical initiator. Radical initiator. What does that mean? A few days ago we talked about chlorine, Cl2 being a stable molecule, but when you hit it with ultraviolet radiation, it breaks it apart. When it breaks apart, you get this. How does this chlorine feel about this condition? Not too good. Not too good. Very unstable. What does it mean by unstable? It means it's angry. It wants to bond with something. It is not going to be good just to go on the rest of its life as chlorine with an unpaired electron. This thing right here, that unpaired electron, makes the chlorine what we call a radical. An unpaired electron is considered to be a radical. So this kind of polymer is only going to be made if we can start it using a radical. We're going to have something that has an unpaired electron in it, very unstable, and that will get a chain reaction kind of going. You have to have an unsaturated compound to start with. Remember, unsaturated means that there's a double or triple bond in there. And let's take a look. We're going to start, bring this down a little bit more. We're going to start with this thing. This is the ethylene molecule. And James, this is going to go back to what you asked earlier. This ultimately is going to make polyethylene. So we start with ethylene. It's got, or also known as ethene. It's got the 2 carbons double bonded to each other. I'm going to pause a moment. If you're writing this stuff down, I want you to write, and then I'll talk in a second. And I want you to be able to listen and walk through this process. Yes. So there's an unpaired electron. That's what the dots represent as an unpaired electron. And then this one winds up with an unpaired in the second step. Yep.
The R means radical initiator.
Yeah, the R represents radical initiator. I know that I use R already to represent some arbitrary carbon chain, but in this case I'm using the same symbol, but to mean a radical. All right, are we good? So here's what happens. Something like a chlorine broken apart from its bonded chlorine is this R value, or not R value, but R character. It's got an unpaired electron. This thing right now is ticked. It wants to join up with something to give it stability. It's not going to stop until it's totally relentless. So when it sees a compound like this thing, sigma bonds, single bonds between the C's and the H's, remember those are local, is directly in between the two bonded atoms. When there's a double bond between the two carbons, there's the sigma bond, and if I could just shade in, you know, that green area that's shaded in right now, that's the sigma bond. Those electrons are kind of protected because they're in between the two carbons. But the pi bond in that double bond, you got some electron density up here and some down there. That is what's vulnerable to that radical. That radical sees those electrons and it wants to grab one and bond to it. So the pi bond breaks. I'll go ahead and break that pi bond. Lose my arrow too, it's fine. The sigma bond doesn't get touched. So you got a single bond, a single electron right there, and a single electron right there. Well, the radical grabs onto one of those. And now how's the radical feeling? Hey, I'm good. I'm good. Everything's fine with me. How is this carbon right here feeling? Angry. This carbon is now angry. And it now is unstable, and it wants some. Is there anything that any other atom can do to help the carbon with the unpaired electron? This group of atoms cannot do anything for that carbon. It's now just going to be angry. So another ethylene is hanging around. This ethylene I think of as a zebra in the Serengeti. And this is the lion. Right? So this thing is going to attack. And that radical goes for that pi bond in that next one. And it's going to attack that. And the same thing is going to happen. Now, this carbon is going to attach to that carbon. And the chain is going to grow. And so this is what it's going to start to look like. Now, we already had two carbons bonded to the radical. Now, this unpaired electron has joined up and attacked this. Now you've got two more carbons. And a single bond was made between those two. That double became a single bond. That's right there. Now we have a new angry carbon. That's going to go out looking. And so this will just continue and perpetuate until there's no more ethylene molecules to find. When all the zebras have been eaten, the lion goes home. He's got nobody else to bond with. So these chains get very, very involved. So it's a different kind of polymer, isn't it? We had polyesters and polyamides making these connections between, where this one, we start with some species that has an unpaired electron, and you have to start with something with a double bond. All addition polymers always start with things that are double bonded together. The pi bonds get attacked, and then you get this chain that starts to perpetuate. Can I show you one more addition polymer? Now you guys are tired today. Gosh, I see people dozing off and sorry.
I'm so confused.
Confused what?
A little bit.
About this? Okay, I'm going to try to walk through another addition polymer with you. It's very similar. And let's see if seeing it a second time helps. What you?
What if you have an acid that has a double bond hole that forms the same type of thing? Additional bond, like CH3COH, and C selective has a double bond.
So complicated.
I don't know. I don't know if that would or not. I've always just seen carbons in the addition polymers, and I don't know if other atoms can wind up doing that. Carbon's nice because it can have 4 bonds. You know, sulfur can't. So that's probably why it's going to be only carbon. All right, now I have uncovered more than I wanted to. I'm just going to start with that. Now, the next simplest polymer that you can have is polypropylene. Polypropylene is going to start with this propene molecule, or also known as propylene, where there's a carbon that's double bonded to another carbon, and then there's a single bond between the middle carbon and the last one. Here comes that radical, and it's ticked, right? It wants something to bond with because it's just not stable the way it is. So there's the double bond. So a similar thing is going to happen with the ethylene. That single electron is going to find one of those pi electrons, and it's going to bond to it. Now remember, that was a double bond. There was already a sigma bond there. It's only the pi bond that gets affected. So these just go from a double bond to a single bond. The R winds up bonding to that carbon, and rather than having 2 hydrogens and 1 carbon attached to it, now it's got 2 hydrogens, a carbon, and this R attached to it like that. It's only gone down to a single bond. Now this carbon, the one that was in the middle of the propylene molecule, that is now a radical. Can this CH3 help it at all? No. It's already got 4 bonds around it. It doesn't have anything to offer to. So this CH3 doesn't really, it can't console this middle carbon. In my mind, what I picture in this case is the CH3 is kind of like the quiet husband, and this radical carbon, that's like the angry wife. Okay, you ever see an angry wife with her husband? You know, what does the husband do? He just like gets out of the way and just stay away from me. I'm not going near you. I don't want any part of this. And you know, the wife is just all angry. I'm not likening this to my own home. My wife is very sweet. Once in a while she goes off, and I do that. I kind of get out of the way. Check out this next step. So you've got the angry wife here and the husband that kind of got up and out of the way, because this thing can't do anything, just like the husband can't control the angry wife. She's just going to be mad. For a while, at least. So that CH3 is now kind of up here and out of the way, and that radical carbon looks for something that can bond to it. Think of a radical as something that's very, very angry, and it's going to have to attack something. So there's a pi bond, and that's what's going to fill the rad. We'll say this is the wife's best friend. She's going to take it. Okay, so this thing is going to come along in here. So what's happening here? We started with a 3-carbon monomer. There's still 3 carbons, but one of those, the single bonded carbon, it can't really do anything, so it just pops up and out of the way, and we wind up with this. Here's our first molecule, and that first one, the middle carbon on the first molecule, made a bond to the end of the second one, and there's the middle one in the second molecule. Both those CH3s that were single bonded just kind of jump up and out of the way so that this chain can continue like that. So propylene, or polypropylene, is going to have, I have it right here. The continuing, the repeating unit is CH2, CH with a methyl group on it. So you get all these alternating methyl groups on the chain. So the presence of a functional group on that chain will change the properties of the plastic. All right, now I have one of the, I know it's the bell rang. Just to summarize, just if you look at this and don't even write it down, you'll always recognize an addition polymer because it's all carbons in the parent. The condensation polymers will have something other than carbon in the parent. Think of the polyester, you got the C double bond O in the parent.
This is a test of the pH.